All right, so in the last video, we talked about limits at infinity for rational functions. So today we're going to go a little bit more difficult, but for that, I want to talk about the function y equals absolute value of x over x. And so what does this function do, and what does the graph look like? Well, what you're doing, you're grabbing an x, if it's positive, you're leaving it as it is, meaning if you say plug in 1 and divided by 1 would give you still 1. Wrong example. Let's choose 2. Absolute value of 2 is going to be 2, divided by 2 is going to be 1. So whenever you have a number that is going to be positive, the function will always take the value of 1. Just plug a few numbers to convince yourself. So say 3. Absolute value of 3 is 3. Divided by 3 again gives you 1. Now, let's take a look at what happens when you move over to the negative side. So if you say pick negative 2. So negative 2, absolute value gives you positive 2. Divided by negative 2 gives you negative 1. So the function will do this here. So give you negative 1. Now, whenever you have 0, you're dividing by 0, so 0 is not in the domain of this function, and so we simply do not define it there. So this is going to be it's often called a sine function, except when you do it the sine, you may take sine of 0 to be 0. In any case, this is going to be important for us. So let's take a look at what happens, for example, if we want to do the limit as x goes to infinity of the square root of x squared minus 1 over x plus 2. Something along those lines. Well, what would happen is we have a bit of a problem, because what we used to do is say, let's look at the largest or the highest degree on both expressions and then multiply and divide by that x to that power. And we have a problem now, because this is not a polynomial. So firstly, I cannot even talk about its degree. And the degree of this one is 1. It's okay. But if you could hope for something, and you could distribute this, which you can't, but if you could operate and take the square root of the x to the x squared, you would end up with an x, right? Well, sort of. But let's say you would end up with an x, right? Okay. So we would say if I have this leading term, quote unquote, is of the order of magnitude of an x, and this is an x, then it would seem like I have to multiply and divide by x. But I'm not going to do that because I have the square root. What I'm going to do is I'm going to multiply and divide by the square root of x squared. And you say, well, that just cancels, and I'll say be very careful with that, because remember that, let me do it as an aside, the square root of x squared, or in general, the nth root of x to the n when n is even, is not going to be x, is going to be the absolute value of x. N is even. Ooh, n is just going to be x if n is odd. So be very careful with that. All right, so when I distribute this in, I can do the same thing as I did before. This goes inside of the square root as 1 over x squared, and I get x squared over x squared. And when I distribute this in here, I get minus 1 over x squared. And this one in here gives me a something of the form x over the absolute value of x, and then plus 2 over the absolute value of x. So at that point, then this one becomes a 1. And then here I get the function I have, or the reciprocal of the function I have there. However, both both functions behave in the exact same way, so I can just rewrite it as x over absolute value of x and 2 over absolute value of x. Now, since I'm going to x to positive infinity on the positive side, this could be considered just as 2 over x. And as such, because I'm only taking positive values, as such, this is going to 0. And this one is going to 0 as well. So now I'm left with the limit of the square root of 1, which is going to be 1 over, and now I have this term right here, which if you look at the limit as x goes to positive infinity in this direction, is going to be a 1. And so our limit becomes 1. So actually, it would be a good thing to record that fact. Limit as x goes to infinity of the absolute value of x, or x over the absolute value of x, is going to be equal to 1. And the limit as x goes to negative infinity of x over the absolute value of x is going to be, you're going to be going in this direction, negative 1. All right, so this limit here gives us positive 1. If we would have considered then the limit as x goes to negative infinity in this case of the exact same function, you would multiply and divide by the same function. And I'm going to do the detail I skipped here just because I felt like I didn't do enough detail for it. But what happens is you can write this as the square root of, and I forgot to write my limit, 1 second. That's very common, by the way, forgetting to write your limit. Don't forget to write your limit. Negative infinity as well. So whenever you put it in, what happens is you can write this as x squared minus 1 over the square root of x squared over, and this one right here I'm just going to write as I had it. This one there is not much to do but to distribute it. But what I did from here to here was to combine this and so I wrote it as a single square root, and I wrote it as x squared minus 1 over x squared. And then I distributed that x squared as you normally would to get this expression here. And now the difference now is that whenever we get our limit going to negative infinity instead of to positive infinity, we would have the square root of 1 minus 1 over x squared over x over absolute value of x plus 2 over absolute value of x. And in this case, this would go to 0 as well. This one you would have to think about it as 2 over negative x, but that's still going to be negative 2 over x, which still goes to 0, so no problem there. But this one right here is the one that is going to change, and in that case it's going to be going to negative 1. So limit will go to 1 over negative 1, which is negative 1. So that would be how you compute these types of limits. Let's do one more and let's see how we do. All right, so let's do another example here. What happens when you have odd powers? So with a cubic root there, and maybe I could have done it to the power of 6 maybe. Anyways, let's now look at if I put any higher power here, then it wouldn't matter. Everything would end up going to 0. In fact, let me show you that that's the case. Let's put a square. All right, so what do you do now? Well, at this point, you would have that this is essentially of degree 1. Remember, you cannot distribute that, so you don't make that mistake. But you think this is a power of 1/3, a power of 3, multiply powers would give you a 1, so essentially is of degree 1. So order of magnitude, if you will. But do not distribute. Please do not do that. So then I have a 2 and a 1, let's call it. So I'm going to pick the 2. So I'm going to do 1 over x squared, and then 1 over x squared here. And now you should be thinking, well, wait a second. I'm going to be doing a cubic root, not just a simple term. So what do I do? How do I change that one? Well, let me tell you how you do it. So the bottom, there's no problem, right? That one, we don't have any problem at all. We just distribute it and we're good. But what happens with this one is the following. Let me write it again. So we're going to write it as 1 over the cubic root of x to the 6th. Because if you think about, and I'm going to finish writing the entire thing so you don't get confused. If you think about what's happening here, this is a power of 1/3. This is a power of 6. When they multiply, gives you x squared. So what about the sign, you will ask? Well, x squared is always non-negative. So right here, this expression will be always non-negative. So we don't have any discrepancy there. So we can write that these two quantities are exactly the same. And why do I do that? Because I want to be able to distribute and put this inside of my cubic root so I can cancel things out and use my properties of limits to make them go to 0 in that sense. So that's very, very important that you write it in the format that you have so that you can distribute it in appropriately. So in this case then, I get the limit as x goes to -infinity. And then I get the cubic root of, I'm going to put this one inside and collect the cubic roots all at once. So I'm going to do a couple steps in one, but I think we've done it enough that it should make sense. Now we distribute this one here. I get 1 x squared over x squared gives me a 1, and then 3 over x squared like that. All right, so what happens then after is that I can distribute this x cubed plus, oops, my bad, I said I would distribute it and I did not distribute it. That's not good. Let's do it. So I get x cubed divided by x to the 6th. I get 1 over x cubed plus x divided by x to the 6th is going to be x to the power 1 over x to the power of 6 minus 1, so 1 over x to the 5th. And then minus 1 over x to the 6th. All over 1 plus 3 over x squared. And so now when you look at your limits, remember the fact that we had that all positive powers of x in the denominator go to 0 as x goes to plus minus infinity. So in this case, we're going to 0, 0, 0, and 0. So in this case, we get 0 divided by 1, which is going to give us a 0. And that would be the right answer. That would not give you a 0 in the exam. So anyways, let's take a look at one more example. And in this case, we're going to be looking at a different kind of function. So what happens, for example, with the limit as x goes to positive infinity of the cosine of 1 over x? So now we have a trigonometric function and a 1 over x. We know that 1 over x goes to 0. And so what we're going to do is we're going to look at the fact that the cosine is a continuous function on the entire set of real numbers. And as such, you can move the limit in and out. So that's given to you by continuity. So you can write this as the cosine of the limit as x goes to infinity of 1 over x. And that limit is 0, so you get the cosine of 0, which at that point, that's 1. So that was an easy one. Whenever you have continuous functions, you have to be careful that you need to have continuity. You can move limits in and out. If you don't have continuity, then please do not do that. All right, so let me do one more, and this is going to be a fact that we're going to use to compute other limits. So the limit as x goes to positive infinity of e to the x is going to be positive infinity. Well, it's a series of facts, I suppose. So limit as x goes to negative infinity of e to the x, that's going to be going down to 0. And that you just have to think about the graph of e to the x, which is asymptotic to the x-axis. And my ink is looking a little bit. Let me change marker. All right, much better now. So if you think about the graph of e to the x, as x goes to positive infinity, you're going to infinity, positive infinity as well. And when you're going to negative infinity, you're going to 0. Then you can do the same for e to negative x, which should be just reflecting this, this graph. So e to negative x will go to 0. And limit as x goes to negative infinity of e to negative x will be positive infinity. But it's easy to remember them whenever you look at the graphs. And so let's compute an example with e's involved. And at that point, we'll find out that we will probably need another rule. And then we're going to talk about that rule that is called L'Hopital's rule. All right, so one last example for this video, where we use the exponential. So let's say that we're going to compute limit as x goes to positive infinity of e to negative x over x. So let's take a look at what happens. So this one we really don't have much of a strategy, but we can tell that this is the product of two functions, if you will, or the quotient. But think about it as 1 over x and then e to negative x. And so from our table here, the limit as x goes to infinity of e to negative x is going to 0, and the function f of x equals 1 over x is going to 0 as you go to infinity. So this one is an easy one because we can split it into the product of two functions whose limits both are going to 0. They don't have to go to 0. They just have to be defined so we can actually write this or separate them as the product. So in this particular case, we have that this one is going to 0, and this one is going to 0. So 0 times 0, still 0. All right, so that is an easy example that gives us one that we can compute. But there's going to be another one, or there's going to be many other types where we're not going to be able to do that. So let's think about, for example, of the function e to the x plus e to negative x over e to the x minus e to negative x, which would be the hyperbolic cotangent, if you will. So this one right here, we would have to do a lot of algebra or a lot of different operations to be able to actually compute it. So it seems like it would be rather complicated. One of those things we could do is, for example, do a common denominator e to the x, because this is a 1 over e to the x if you think about it that way. Let me write it in detail. Minus. And you could now do a common denominator. And you would have an e to the 2x plus 1 over e to the 2x minus 1 after you simplify. I skipped a couple steps there. But that still leaves you in a bit of a pickle because you don't really know how to deal with it, because this term is going out to infinity. This is going to infinity as well. And at that point, you say, what do I even do? And we will have a solution for you, but it's going to be called the L'Hopital's rule. So we'll learn that in yet another video. So there are some limits where you will, with the rules that we have, when you're going to infinity or to 0, you will not be able to compute as easily, but we will have a rule that will help us compute them. But that will involve differentiation, so you will learn that in later videos. All right, so we'll leave it at that for this one, and I'll see you in the next one.